champions. Today we will see linearly independence and basis part 1. First of all, we will see definition of linear combinations of vectors. V is a vector space. Okay. If you take any element from the vector space, that is called as a vector. Now, let us suppose I am taking n vectors from vector space V. So, whatever the number of elements from the V I have taken, take same number of scalars from the field F. So if suppose I have taken n vectors, then I have to take n scalars denoted by alpha 1, alpha 2 and so on up to alpha n. And if you take multiplication of one scalar and one vector, since V is a vector space, this scalar multiplication is again a member of V. So again alpha 1 V1 is a vector, and addition of vectors may allow, because V is a vector space, if we multiply each vector by each scalar and if we add them, whatever addition we will get, that expression is called as linear combination of these vectors over the field F. Therefore, we define if V is a vector space over the field F, and if V1, V2 up to Vn belongs to V, then any element of the form alpha 1 V1 plus alpha 2 V2 plus up to alpha n Vn, where no doubt alpha 1, alpha 2, alpha n are the members of F. This expression is called as linear combination of vectors V1, V2, Vn over the field F. Now let us see the another definition, linear span. Okay. If S is a non-empty subset of a vector space V, we don't know how many elements are present in the vector space, and therefore we cannot predict how many elements are present in the subset S. But still we taken one subset which is non-empty of the vector space V. Okay. Now linear span of S denoted by L of S is nothing but the set of all linear combinations of finite sets of elements of S. Here the word finite sets is present because we don't know. S is, no doubt it is a subset of V, but we do not have any guarantee that S containing finite number of elements or infinite number of elements. Hence, for taking the linear combination, we need some finite elements. Therefore, we are considering subsets of S which are finite, and then we will take linear combination of all the elements of that subset, and that linear combination, if we collect in a set, that set is called as a linear span, and it is denoted by L of S. After these two definitions, let us prove one result. Prove that linear span of S denoted by L of S is a subspace of vector space V. S is a subset of V, and therefore L of S is also a subset of V. This is the first condition we need to prove that subspace. पता है आपको कि सबस्पेस प्रूव करने के लिए आप जिसको भी सबस्पेस प्रूव करना चाहते हो वो V का सबसेट होना जरूरी है। तो यहां पर हमने ये प्रूव कर दिया कि L of S is nothing but a subset of V. Now the only question remaining to show that L of S is a subspace of V. चलिए बताइए कि किसी भी सबसेट को V का सबस्पेस अगर प्रूव करना है तो क्या करना पड़ेगा। तो पहले दो एलिमेंट लीजिए, फिर दो स्केलर लीजिए, फिर उन दो एलिमेंट का लीनियर कॉम्बिनेशन लीजिए और वो लीनियर कॉम्बिनेशन अगेन अ मेंबर ऑफ L of S प्रूव कर दीजिए, तो L of S सबस्पेस हो जाएगा V का। To show that L of S is a subspace of V, that is to show that alpha x plus beta y belongs to L of S for every x y belongs to L of S. तो इसके लिए पहले x और y आपको लेना होगा L of S से। Let x y belongs to L of S. Now x is a member of L of S, that means can be written as a linear combination of some elements of finite subset of S. So we may write x is equal to alpha 1 v1 plus alpha 2 v2 plus up to alpha k, and y can be written as another linear combination beta 1 w1 plus beta 2 w2 plus beta l wl, where these sets v1 v2 vk are finite subsets of S. This w1 w2 wl is a finite subset of S according to definition of linear span. Now let us consider two elements alpha and beta which are scalars, means these are the members of field F. Now we have to show that this element is a member of L of S, therefore consider alpha x plus beta y, put the value of y here. Now multiply this, you will get this expression. Since alpha and alpha 1 both are scalars, therefore alpha into alpha 1 is a scalar, alpha into alpha 2 is also scalar, and lastly this beta into beta L is also a scalar. And no doubt this is a linear combination of v1, v2, vk, w1, w2 up to wl. Since these elements, if we put in one set, and this is a finite subset of S, therefore this linear combination is a member of L of S. And this linear combination is equivalent to alpha x plus beta y. Therefore, alpha x plus beta y is a member of L of S for all x y belongs to L of S, and alpha beta are the scalars. We have proved alpha x plus beta y belongs to L of S, hence L of S satisfy the condition of the subspace. Hence L of S is a subspace of vector space V. Now move to the another result. If S and T are subsets of vector space V, then prove that S is a subset of T implies linear span of S, that is L of S, is also a subset of linear span of T, that is L of T. So in this result, it is given that S is a subset of T. Let me call this expression is an equation number 1. Now we have to show that we mention in the claim to show that L of S is a subset of L of T. That is to show that every element of L of S is again a member of L of T. So consider one element from L of S. Let us give name, that is X belongs to L of S. And finally we have to show that this X is again a member of L of T. Now right now this X is a member of L of S. Therefore X can be written as a linear combination alpha 1 V1 plus alpha 2 V2 plus up to alpha k Vk, and where this V1 V2 up to Vk is a finite subset of S. Always we are writing this because of the definition of L of S. But from equation 1, in that equation we have already mentioned that S is a subset of T. Now this set is a finite subset of S. S is a subset of T. So automatically by transitive law, this V1, V2, Vk, this is a finite subset of T. Also, linear combination of the elements of that finite subset, that means linear combination of V1, V2 up to Vk is in L of T, and that is the linear combination of V1, V2, Vk belongs to L of T. Why this is in L of T? Because already we have proved that V1, V2, Vk is a finite subset of T. So automatically its linear combination is a member of its linear span, that is linear span of T. And this linear combination is equivalent to X, therefore X belongs to L of T. So in this result we have proved that every element of L of S is a member of L of T. Hence L of S is a subset of L of T. Okay, alright. Next result, if S and T are subsets of vector space V, then prove that L of S union T, that means linear span of S union T, is equal to linear span of S plus linear span of T. We have to show that equality, hence we have to show that left side is a subset of right side, and also we have to show that right side is also a subset of left side. So in the proof we have mentioned that we have to show that L of S is equal to L of S plus L of T. That is to show that this union span is a subset of addition, and the addition is a subset of L of S union T. So first we will prove the first subset relation. So let X is any member of linear span of S union T. So it is a member of linear span, that means that element can be written in the form of linear combination. So we have taken X is equal to linear combination of V1, V2, Vk and W1, W2 up to Wl, where this set of vectors which are present in the linear combination is a finite subset of S union T. This is according to definition of linear span. But purposely we are taking these vectors in such a way that some vectors, first k vectors V1, V2, Vk is a finite subset of S. Purposely we are taking this, and W1, W2, Wl is a finite subset of T. So therefore, so this V1, V2, Vk is a finite subset of S. Therefore, linear combination of V1, V2, Vk is a member of L of S. We have mentioned here. Since W1, W2 up to WL is a finite subset of T, therefore its linear combination belongs to linear span of T. It means that when we add these two linear combinations like this, so this is a linear combination from L of S, this is a linear combination from L of T, we have taken its addition and that addition is a member of L of S plus L of T. And this addition of two brackets is nothing but X, hence X belongs to L of S plus L of T. And here we have proved that every element of linear span of S union T is a member of L of S plus L of T, hence L of S union T is a subset of L of S plus L of T. Let me call this expression is an equation number 1. Now we will prove that addition of two linear span is a subset of linear span of union, and once we will prove it, then we will call it as equation number 2 from 1, and from equation 2 we will prove the equality. Now we will show that L of S plus L of T is a subset of L of S union T. For this purpose, we have to take one element from the left side. So let us consider that element is X. So let X belongs to L of S plus L of T. Now this X can be written as Y plus Z, where Y is a member of L of S and Z is a member of L of T. Since Y is a member of L of S means linear span of S, therefore that Y can be written as a linear combination alpha 1 V1 plus alpha 2 V2 plus up to alpha k Vk, where V1 V2 Vk is a finite subset of S. Similarly, Z is a member of L of T. Therefore, Z can be written as a linear combination of W1, W2, WL, where this set W1, W2 up to WL is a finite subset of T. Now, therefore, this set containing V1, V2, Vk, W1, W2, WL, all the elements are these two sets, and this is a subset of S union T, and this is no doubt it is a finite, and therefore linear combination of all the elements of this set is a member of linear span of S union T, and hence this linear combination is nothing but Y plus Z. Therefore Y plus Z belongs to L of S union T. Y plus Z is nothing but X, so X is a member of S union T, and therefore L of S plus L of T is a subset of L of S union T. Let me call this expression is an equation number 2. Already we have proved in equation 1 L of S union T is a subset of L of S plus L of T. Now we have proved in equation 2 another subset relation, and hence from 1 and 2 we have proved the required result.